Okay, we start our session. In this session, we are going to talk about chapter 8. Okay, so it's random signals with unknown parameters. So in this chapter, we will discuss the detection of a Gaussian random signal with unknown parameter in white Gaussian noise. Let's recall what we did previously. We have been talking about deterministic signal, right? Deterministic signal, meaning that the signal is either known or unknown, but it's deterministic in nature. So uh, we don't think of that model as anything random other than the noise. And now there is not only the noise, but also the signal itself is random. Okay? So although we restrict our discussion to white noise, the color noise problem is a simple extension. One need only pre-whiten the data, assuming noise covariance matrix is known, to reduce the problem to allow a Gaussian random signal in white Gaussian noise. So we generally assume the signal is zero mean. Is the signal covariance is not completely known. So the point is the signal covariance matrix. As we will see, this creates difficulties in determining the MLE, and the subsequent GLRT is also difficult. Okay, so generally speaking, we are going to deal with random signals as opposed to deterministic. So, so we first attempt to determine the GLRT for a signal with the covariance matrix known except for scale. The MLE is found by minimizing something, which we'll talk about later, which unfortunately cannot be done in closed form. For the special case of white noise, the MLE is given by this. Another case of interest is the rank 1 signal covariance matrix, for which the MLE is given and the GLT is available. Okay, so let's uh, move to here. So 8.3 in completely non-signal covariance matrix. So in general, the Bayesian approach to this problem proves to be mathematically intractable due to the required integration. The GLRT, on the other hand, is more analytical and manageable. As a last resort, the required MLE for the GLRT can be found numerically. Therefore, we will concentrate on GLRT approach. The general problem is to detect a Gaussian random signal in WGN for this. So H0 you have noise only, and then H1 you have signal plus a noise, where Sn is a Gaussian random process. It's no longer deterministic anymore. Okay, so it's a Gaussian random process with zero mean and covariance matrix CS. And Wn is the white Gaussian noise with variance sigma square. The signal covariance matrix depends upon some parameters which are unknown. Okay, so here's the point. The signal covariance matrix depends on some parameters which are unknown. As an example, we might not know the power of the signal. If the Sn is y Gaussian, y sense stationary, then this is equivalent to not knowing RSS. RSS is the time deviation, the autocorrelation function of time equal to 0, which means the process without time deviation. the correlation with itself without time deviation. So that's 0, RS is 0, and that's expected S squared. Notice that we will be able to talk about this expect S squared only if S is random, right? If S is not random, we are not talking about the expectation of itself, because it doesn't mean anything to talk about the expectation unless it is random. So now the difference is this is random. Okay, so n equal to 2, the signal covariance matrix is like this. You have CS equal to RSS 0 and time deviation 1, time deviation 1. And then this is RSS 0 taken out, and this is low. That's the correlation coefficient. So if you take one coefficient RSS 0 out, this becomes 0, 0, 1, 1, and low, low. So this is low equal to RSS 1 divided by RSS 0. It's a correlation coefficient. Hence, the PDF on the H1 is P of x. On the H1, P of x RSS0 on the H1 equal to 1 over 2 pi determinant. This is what? This is a vector version Gaussian distribution. Okay, recall it's a vector version, and then Gaussian distribution with covariance matrix CS plus sigma square I. How come it's sigma square? It's CS plus sigma square I. Because you recall you have S, right? S contributes to covariance CS, and then this Y Gaussian noise contribute to sigma square I. Okay, so as a result, the total covariance for X is CS plus sigma square I, which is this. Okay, it also the denominator of here. Okay, and there is a minus inverse, not inverse, but minus to the minus one, meaning that this is yeah, it's a matrix inverse. It's an inverse of the matrix. It's almost equivalent to putting a scalar in the numerator, in the denominator. Putting a scalar in the denominator, equivalent. Okay. So to implement a GLRT, we must maximize this over this to find the MLE, right? This is the GLRT framework. You maximize the likelihood and then over some parameters. And once that parameter is found, it's a MLE. Yeah, because of the need to analytically evaluate a determinant and inverse of a covariance. This may be difficult. In general, when a signal covariance measure depends on several unknown parameters, the task is even more demanding. We generalize this example next. So, okay, let's take a look. Unknown signal power. Consider the detection problem where Gaussian random signal is zero mean and has covariance CS P0 C with P0 unknown and C known, meaning that the signal is only unknown in its power P0, but the structure of the covariance is known. The previous example is a special case in which P0 is RSS, right? Let's take a look. Right, this thing is RSS multiplied by this, but it's C this, and then P0 is RSS 0. That's a special case. Hence, we know the signal covariance matrix to within a scale factor. The PDF on the H1 is, we have it already, and we just have to put the P0 in. So you have P0, Okay, 2 pi to the n divided by 2 determinant 1/2 p0 c plus sigma square I exponent this and that. Okay. To implement the GLRT requires us to determine the MLE of P0. The determinant and inverse of the covariance can be easily found if this is first diagonalized. And one way to accomplish this is to utilize eigen decomposition. Okay, recall linear algebra. Let's do eigen decomposition, eigenvector, and eigenvalue. Okay, since C is symmetric and positive, definitely we have this, and hence C can be decomposed into determinant of P0 C plus sigma square I equal to this, equal to that, equal to this. And eventually, since it becomes diagonal, it becomes a multiplication. Okay. So recall, if you have something that is diagonal, and 0 elsewhere, diagonal means that only diagonal axis has elements. And you want to take the determinant, which is going to give you multiplication of all those things, right? So it becomes a multiplication of all those lambda I, right? That's the lambda I. So it's the same thing. You have P0 lambda becomes P0 lambda I plus sigma square, and then you multiply together. Okay, and also we have the inverse. Inverse, when you do the eigen decomposition, the inverse is easier. It's easier. So you put it into this form and this form and then this form. The inverse is easier. And from 8.3, we have this LMPX P0 H1 equal to something like this, equal to something like this. And you see there are eigenvectors and eigenvalues involved. Okay, and then since this is this, and this is a diagonal matrix, to find the MLE, we must minimize. Minimize what? Minimize, we want to maximize this, right? We want to maximize this. And to maximize this, you have minus sign somewhere. Some irrelevant terms are cancelled out, right? Irrelevant. If something is irrelevant, they are cancelled out. And then this term stays, and it goes to here and here. And how come it becomes minimized? Because you want to maximize this, and you have minus sign. Once the minus sign is there, you take it away, and max becomes min. Right? Max becomes min by taking the minus sign away, so it becomes minimized. And then we call it the function of j, and it has variables p0. And remember that lambda doesn't matter. Lambda is not variables in this case, because lambda is the eigenvalue of c, but c is considered known in this case. C is available, and therefore eigenvalues v and eigenvectors lambda are all available. So lambdas are available, v are available. X is your receive signal, and the variable becomes only p0. And then you know you want to find minimization of this j over p0, and then what you do is we do differentiation of j, derivative of j. Okay, but derivative says that it's complicated, so the solution is still unknown. But I think one thing to do is, if we just come up with the equation, we even if we cannot do derivatives, we can do some numerical approaches, or we do some random search or genetic algorithm, that kind of stuff. Then eventually to find the minimum value of J through a single variable P0 isn't difficult. It's not difficult. Okay. You can even do bisection approach. Right? A lot of different approaches to find the max or min. And then unknown signal power. If all i's are equal and say it's lambda, then the J, you see the J, lambda I becomes lambda, and then it will simplify, right? The whole thing, lambda I becomes lambda, equally weighted lambda. Okay. And then we do some derivation. This thing is like this thing. So that JP0 going from here is like this. You have N Ln P0 lambda plus sigma square plus xtx over P0 lambda plus sigma square. And lambda is a single variable. So this corresponds to C V lambda V inverse lambda I. Or the random signal is white. White means that its covariance matrix is only non-zero in the diagonal. That's called white noise. By definition, that's called white noise. So we have, upon differentiation, we get this. Right? You take derivative. Again, we want to minimize this, right? And the way to do it is to take derivatives. And take derivative, since lambda I is becoming a single lambda value. So take differentiation is available. It's available. Now, you just solve the equation, right? This is a first order derivative. Think of it this way. This is a first order derivative of, P0. The first order derivative of P0. And then you set it to 0, you solve for it, you get this P0 head. As long as P0 head dies, as long as P0 head larger than 0, if however this is smaller than 0, what that means is even you get the best value for